Hey students, this is your Professor Omelianchuk, and we're going to finish up our unit on normal form and circuits. And so we talked a little bit about what the gates looked like the other day, and so you can revisit that lecture if you want to check those out again. But basically what I'd like to do here is revisit how normal form works and what it is and how it can be useful to us in the analysis of word problems that we're going to be looking at for digital circuitry. Okay, so here's the deal, all right? Just to review, there's different ways of expressing normal form, and the one that we're the most familiar with is disjunctive normal form. Right? A formula is in disjunctive normal form if it is a disjunction. And the disjuncts are made up of smaller disjunctions, conjunctions, negations, or atomic well-formed formulas, right? So basically no arrows allowed, and that's really kind of, that's a good thing. It's a nice form to have, especially when you're using digital circuitry, because there aren't any arrows allowed in digital circuitry. So we're going to be making use of normal form, okay? Of course, there could be a conjunctive normal form, right? It's the same sort of thing as disjunctive normal form, except the only difference is that the main connective is a conjunction. Negated normal form or negative normal form is just, it's the same thing, right? Again, right? Conjunctions, disjunctions, negations are atomics, but the main connective is a negation, right? So like I said, no arrows are allowed, which is really good for digital circuitry because it also has no arrows allowed. All right, so here's a circuitry problem that we might encounter, okay? So what we have are two inputs, right, A and B, and whenever A is 0 or off and B is on, or B is off and A is on, the circuit outputs an off, okay? Otherwise, it outputs an on, okay? So what we're going to do is we're going to draw a circuit that performs the operation, okay? So that's what we want to do. Now, how are we going to do this? How are we going to achieve this goal? Right, here's the means to doing that. First step, we're going to write down a table of operations for the circuit as specified by the word problem. Then what we're going to do is we're going to write down a sentence of the operation described in the table in what will be disjunctive normal form. And that's assuming there's going to be two outputs that have one. It depends on what you have, right, in the circuit, okay? And so we'll think hard about that as we go, okay? So basically what I'm gonna do is I'm just gonna create a table of operations. Now I only have two choices here. I got A and B, right? So I'm gonna have 4 different possible ways that those things could be combined. It's the same sort of truth table rule that we used in TFL, right? How many choices you have. So you can have that little formula, 2 to the n. And so we have 2 choices here. 2 to the second power is 4. And so you arrange things like so. All right, so the rightmost column is, the 1, 0, 1, 0 pattern. And then it's 1, 1, 0, 0. Okay? All right, so now we got to figure out what the output is going to be given the inputs. All right, so let's just take a look at the word problem again. And it says that whenever A is 0 and B is 1, or what I'd like to do, this is what I'm doing here, is I'm just kind of not paying attention to the or here. I just want to take a look at like the first condition, all right? So whenever A is 0 and B is 1, the circuit outputs a 0. So okay, that's helpful. I'll just go to that particular scenario there, and I'll put a 0. Okay, that's line 3 or row 3. And then I just go to the next part of that disjunction there. Whenever B is 0 and A is 1, well then I get a 0. Okay, so there's the 2 zeros, and then it says otherwise it outputs a 1. And so now, right, I have the whole table filled out. All right, I have the whole table filled out. Okay, so now what I'm going to do is I'm going to create a normal form sentence that captures the output values that say 1. Right, so just like in normal form where we were capturing the output values that say true, we're doing the same thing here. Whenever it says 1, we want to capture those. So let's do that. So both A and B are 1 in row 1, so we want to get that. And then both A and B are 0 in row 4, and we want to capture that. And we're going to use negations to capture the zeros, just like we use negations to capture falsehoods in TFL. Right? So those are the two formulas that give us ones, and that can create a disjunction like so. All right? So that's a sentence that we can use now to represent the outputs. Right? So then how on earth do we draw a circuit? Well, this one's relatively simple. All right, so what you do here is you can just actually kind of start with the main connective, all right, and just identify that with your output gate, and then hook it up to the two AND gates like so. And just note that one of the conjunctions there has to pass through, both of its wires have to pass through two NOT gates before they get linked up to A and B. Right, and so everything gets linked up to A and B somehow there, and that's how I drew it, right, in my Microsoft Paint program. So I'm sorry for the kind of crappy drawing. That's what you get when you use Microsoft Paint. All right, and so that is a way of drawing it. That was very simple, okay? And so that whole process is just what I'm going to be asking you to do in the word problem. All right, so for now, we might be asking this as engineers: is there any way that we can make this more efficient? Right, so I actually want you to kind of think about this a little bit, right? And, maybe pause the video and try to think it through, right? The easiest way to do this is to just analyze what the output gate is saying and see if you can detect a pattern there that can be represented more simply given the gates that you have. So if you've taken some time to think about that, just think about the XOR gate for a moment and notice how the output value on the XOR gate says 0, 1, 1, 0. And this says 1, 0, 0, 1. And just look at the relationship there. I mean, this is saying like the exact opposite of this, right? You can kind of see that, right? And so what you could do is you could actually take the XOR gate and its output and negate the output of the XOR gate. And you could get the exact same, output given the same inputs, right? You'd have a logically equivalent circuit, but has a smaller size and depth, right? So if we go from a size of 5 to a size of 2 and a depth of 3 to a depth of 2, that's pretty good, okay? All right, so here's a more complicated problem, right? Here we have 3 inputs, A, B, and C. If either A and B or A and C are both 1, then the circuit outputs a 0. It also outputs a 0 if all inputs are 0, otherwise it outputs a 1. Okay, so what you have to do is go through the same steps, all right? So A, B, and C, that's 3 choices, so you're gonna have 8-row table of operations, and then you just have to follow the directions, right? So take a minute and draw that up, all right? You can pause the video, work that out, right? And then you should come up with something that looks like this, all right? You should have 4 places where you end up with a 1. And now you have to capture these in normal form. So here you have A and not B and not C. Or you have not A and B and C, or not A and B and not C, or not A and not B and C. All right, so that's a pretty complicated sentence. All right, you actually are going to have, I actually made it well formed here. This is the main connective right here, just so you know. And the reason I made it well formed is I wanted to pair things up to kind of keep track of the way our circuits work. All right, so circuits, remember, they have a pair of wires, except for the NOT gate, that just attaches to 1, right? But they have a pair of wires as input, and then they spit things out as a single output, right? So I like to have the pair of things recognized. Now, you have to remember conjunctions are associative, so you could draw it up. You could put the brackets around the not B and the C. That's okay. You could do that just as well. I just kind of did this for, just kind of my own organizations. I like to kind of have the A and B's together. All right. So when you're drawing this, there's different ways you can do this. I'm going to do this the hard way because this is the way that I originally did it when I made the slides, right? I can show you an easier way. I think in the next lecture I talk about this, and so we can talk about. You can actually visit that lecture and see the easier way of doing it. But this is the hard way of doing it, right? And I don't really recommend this because it gets too hairy and it gets too complicated, right? But basically, what I'm doing here is I'm working from the main connective. I'm working from the outside in, basically. So here I attach then to the other two ors, then I attach to the four ands, all right? And now this is where this gets just to be totally crazy, all right? Now I'm attaching to some ands and to some knots, okay? And then I get all the other knots in there, and oh my gosh, it is just a mess. I mean, look at that thing. That is just horrifying. It has a size of 18 and a depth of 5. And that is just, ugh. Now, I'm not going to, you don't have to draw something quite this complicated. I think on the homework it's a little complicated, but I'll show you an easier way of drawing it so that you can kind of figure out what to do, right? But that is basically how it ends up drawing. You can see how complicated this gets, right? So it's pretty big circuit, pretty messy, all right? I'll just kind of tell you, is there a way to make it more efficient? And the answer is yes. I'm not going to go into this in great detail, right? It ends up being it ends up being equivalent with that particular formula, right? And you might be wondering how I got that, and I'll just kind of briefly explain the method to you. You don't have to learn this. This isn't on your final. This isn't on your homework, right? But this is just the process that I just kind of briefly want to explain as I kind of get into this, right? There's a unit on logical equivalence. We're actually not going to go over it in this class, but there are some equivalence relationships that you should just understand. And here they are, right? So you have things like a commutativity, right? So P and Q says the same thing as Q and P, right? So that kind of makes sense. Associativity, we've gone over that one, like P and Q and, P and Q and R, right? It's going to say the same thing no matter where you put the brackets. Right, there's the distribution type property. So you can kind of see here if you have a P and Q or a P and an R, well then that just says P and Q or R. Right, so you can kind of make things a little smaller, right? You can go from something that looks like this to something that looks like this. Right, there's De Morgan's law. So if you have something like this, not P or not Q, that actually is equivalent with not P and Q. If you think about that for a moment, you'll see why. And you can use a NAND gate, right, to substitute for this. Okay, so you can kind of see how this works. These are somewhat useless because these have to do with the arrow relations. So these are the ones I'm kind of focusing on here. And in order to get right in order to get to this, like how did I go from this big long formula to this? Well, what I actually did is I invented my very own derivation language. All right, and I don't have the rules specified for you. I'm just showing you this. All right, I'm not asking you to do this. All right, so just please be advised. But what I want you to understand about this just total mess here is that each line is logically equivalent with the line above it. So logical equivalence is preserved all the way down. Now I do a little subderivation here for certain purposes. All right, but each line, right, is logically equivalent with the other until I get to the bottom one. All right, and now you might be thinking, wait a second, I see a double arrow in there, Professor O. I thought you said that wasn't allowed, and you're right, it isn't, right? But let me just show you how this is drawn, okay? All right, so the main connective here is an AND. So the AND gate is the output gate, right? So that's what I draw, and then it is then connected. What is the AND connecting? Well, it's connecting another conjunction and a disjunction. All right, so that OR there is captured by the OR gate, and this right here. This is actually that's not a conjunction. I forgot. This is a negation of a conjunction, which translates into a NAND gate, right? And then this whole big monstrous looking double arrow there is actually a form of an exclusive OR, right? That's a way of writing an exclusive OR, and so this ends up being the circuit that is more efficient, and it has a size of 4 and a depth of 3. Okay? All right. That was a lot of information, and a lot of it was irrelevant. All right? I want you to understand that doing this kind of thing is not something I require of you at all. All right? I'm not requiring you to do anything like this. What I'm wanting you to understand, though, is just how you can draw a circuit from, right, the normal form sentence like we did here. Okay? That is basically what I'm going to ask you to do. And you can do it, all right? Trying to get to where I want to go, right? Let's just take a look here. Let's work on this together. Actually, I'll go through this with you, right? Here you have two inputs, A and B, and whenever A is 1 and B is 1, or A is 0 and B is 1, the circuit outputs a 0. Otherwise, it outputs a 1. All right, so just kind of paying attention to the words there. Whenever A is 1 and B is 1, or A is 0 and B is 1, you get a 0. So let's just represent that, okay? And then otherwise it outputs a 1, so there you go. Okay, there you go. All right, so that's your table of operations, and then the two places where it shows up as 1 look like so. All right, so now we're going to draw our circuit, okay? And so the main connective is an OR, so we're going to have that be our output gate. It's connected to two AND gates. And then we have both of the wires in one of the gates is being negated like so. So we got those represented. And then one of the wires is not negated. That goes straight to A. So that's good. And then we have a not B. Okay, so there you go. You have the circuit drawn. Okay, that's done. Right? Now, can you make it more efficient, right? And the reason I ask this is, I think one or two of you, I don't remember now, are some engineers, and you might be interested in this, right? And so this is like an extra credit portion on the homework, all right? Is trying to make things more efficient. So for those of you who are just like, I don't know about this efficiency business, right? Don't worry about it. Okay, this is a logic class. It's not a design class, right? But this is something that engineers work on, right? Is trying to make things more efficient. And so it does involve this kind of analysis, right? This is why logic matters in real life. It's for people like that. All right, so taking a look at the output table, I mean, do you see anything kind of distinct about it? Right? Do you see anything kind of distinct about it? And here's the pattern I want you to recognize. Look at the B column. It says 1, 0, 1, 0. And this says 0, 1, 0, 1. And that's just the opposite, right, of B. And so what you can actually do, and the designers can do this, right? We logicians, we don't think this way, but you can just say, you know what, we don't need A. So programmer guy, right, who thought that we needed an A input is actually just an idiot, and we can ignore him, and we can just erase the A input completely from the analysis and only pay attention to B, because B is the only thing that's doing any work here. Right? So if this sort of thing happened, the engineer would go back to programmer guy and say, why did you do this to us, you fool? And make it simpler. Okay? So there you go. Right, here's another problem we can take a look at. All right. I'm just going to give you the table of operations and have you draw the circuit. All right. And have you draw the circuit. Now, this is the circuit I'm going to help you draw in the next lecture in a simpler way. All right. What I taught you in this lecture is the more complicated way. So when you look at the next lecture, you can see how I do it in a simpler way. Right. And so there is the complicated way of doing it. All right. It ends up looking like this. It's got a size of 15 and a depth of 5. You can make it more efficient. And, I did my little proof here, which you won't understand. All right. This is just my own kind of thinking. All right. This is what logicians do, right? They kind of make up their own little languages to perform the certain functions. And the function I was just trying to go for is making things equivalent all the way through. Right. And so this is what the more efficient one looks like. Right, so that is the lecture. All right, I know, again, you don't need to worry about efficiency. All I care about is trying to draw the circuits and map the normal form sentence to a picture that captures what the circuit looks like. All right, so if you have questions, let me know, and I will talk to you later.